Okay, we're looking at this question, which is really on shapes of molecules. Let's get into it. Okay, it's quite a difficult one on shapes of molecules and a bit of an unusual maths question here. So question five, the molar enthalpy of vaporization, delta H with a little VAP, of a liquid is the enthalpy change when 1 mole of a liquid is converted to vapor at the boiling point of the liquid. Student does an experiment to determine the enthalpy of vaporization for water. The student places a large beaker on a balance. They pour 500 centimeter cubed of water into the beaker. They use a 2.4 kilowatt heater to raise the temperature of the water to 100 degrees. Remember, they said to boiling point. They record the mass of the beaker and hot water. They use the 2.4 kilowatt heater to boil the water for 100 seconds. Um, they record the mass of the beaker and the remaining water. The loss in mass is 103 grams. Calculate the enthalpy of vaporization of the water. 1 kilowatt equals 1 kilojoule per second. And down here, this is a real big clue. Our enthalpy of vaporization is in kilojoules per mole. I always like to look at that because what that tells me is that you need to work out the joules or convert them to kilojoules or work out the kilojoules. And then the mole to the -1 means divide by the moles. So your aim is to look at the units in these maths questions. They tell you what you got to do. Work out joules first, then divide by the number of moles. Okay, so let's see if we can do that. I mean, at first you might look at this and think, is it a Q equals MC delta T? But we haven't been given the specific heat capacity. We haven't been given a change in temperature. We've just been told it boils at 100. They haven't told us the start temperature is 0 or 25. So we can't do delta T. So you can't use Q equals MC delta T for this. And in fact, what they have told us is that 1 kilowatt is equal to 1 kilojoule per second. So we can get bang on that straight away. Let's work it out. So let's get into this. All right, we're looking to work out kilojoules per mole -1, which means kilojoules divided by moles. So let's work out the kilojoules. We've got a 2.4 kilowatt heater. Now, what does it tell us there? 1 kilowatt equals 1 kilojoule per second. So we know we were burning off 2.4 kilojoules per second, right? How long did we do it for? We did it for 100 seconds. So what's the total amount of joules we did? We did 2.4 kilowatts for 100 seconds. So we want to times that by 100 seconds, and that's going to give us 240 kilojoules. Now, the fact that you've got divided by seconds and we're timesing by seconds means we can get rid of the seconds. So we're left with 240 kilojoules. Now all I need to do is divide this by n, which is number of moles, and I'll have my answer. So let's give ourselves a nice little mark for that. Right, the next thing, vaporization of water. Oh, we've got mass, haven't we? Look, we've got a loss in mass. Well, what's being lost? Well, it's just pure water in the beaker. So it's water that's evaporating. So we actually know how much water we used. So we've got mass, we've got MR, and we've got times moles. So I need to do mass divided by the MR. And you should all know the MR of water, just 103 over 18, and that is going to give us our moles. So let's work that out. That's five something five. My maths isn't good enough to work that out without a calculator. 5.72. So recurring. So we've got 5.72 moles of water have been lost, right? So what I want to do is 240 divided by 5.72, and that should give me my answer in kilojoules per mole. But 41.9. Now, how many decimal places do these guys want? It doesn't say. I'm going to go for 2. So I've got 41.941. So I'm just going to leave it as 41.94. And that is my kilojoules per mole. So I'm going to get a mark here for working out the moles of water and then a mark for my final answer. Boom. Right, let's move on to the next part to the question. I did say this question was about shapes of molecules. Well, it's going to come in here a little bit about shapes of molecules and intermolecular forces, this next bit to the question. So let's zing on to this. Table 2 shows some data about three compounds that all contain the same number of electrons. So that is kind of key. And we'll look at that in a second. That's a clue for something later. We've got compounds here. So if I type the names of these, hopefully you know the name CH3, CH2OH. That's going to be ethanol. And then we've got CH3, CH2, NH2. That's going to be ethyl amine. This is like a dimethyl. Yeah, so something like that. Right, let's get into this. So all three compounds in table 2 are polar. So these are all polar molecules. Ethanol is the most polar. So they're giving us a clue here. Ethanol's the most polar. Ethylamine is the least polar. So that's that one. Ethanol's most polar, that's least polar. Explain why all three molecules are polar. So we're going to get a mark. This is the command word. So this is where you're going to get your marks and how you frame your question. So the command is explain why all three molecules are polar. I imagine that's one mark. And while ethyl amine is least polar, that's going to be a second out the 4 marks. So while ethyl amine is least polar. In your answer, refer to shapes. So if you say what all the shapes of those molecules are, that's the third one. And the relative negativities of the most electronegative atoms. So talking about electronegativity as well. So these 4 black lines I've made in this last paragraph are the 4 marks we need to hit. So explain why all 3 molecules are polar. So what is it that all 3 molecules have that makes them polar? Well, hopefully you can see, like, if you're ethanol, you've got the electronegative oxygen and the positive carbon and hydrogen. Methylamine, it's got the electronegative nitrogen, and then these hydrogens are going to be left delta positive and the carbon delta positive. So we can see the electron cloud is being drawn from those bonds around that atom there. And of course, the dimethyl ester has oxygen with carbon on each side, and that is going to be also electronegative there. So the fact is they all have electronegative atoms that are drawing the electrons towards them, and this makes them polar. So all 3 molecules are polar. I don't get a mark for saying that because that was actually in the question. So you might say to yourself, this is a bit of a stupid thing to type. So all 3 molecules are polar. What do we want to say? So I want to say ethanol and CH3O CH3 both contain O, C, and O H bonds. O is more electronegative than C or H. So this makes them polar. Nitrogen is also electronegative, more than C or H. And so ethyl amine is also polar. However, ethylamine contains nitrogen, which is less electronegative than oxygen. So the nitrogen's less electronegative than oxygen. This makes ethylamine the least polar. So essentially, they are all polar molecules because they contain oxygen and nitrogen, which are electronegative. However, ethylamine is the least electronegative because the nitrogen is less electronegative than an oxygen atom. And that's why ethylamine is the least polar. The difference between the electronegativity of nitrogen and carbon and hydrogen is less than the difference in electronegativity between oxygen and carbon and nitrogen. So we've covered like 2 of the marks here, and we've explained why ethylamine is the least polar. We've explained why all the molecules are polar, but also something else to talk about the polarity is the shapes, because if the if the molecules were symmetrical, uh, they would not be polar. However, they are all not symmetrical. Now, you might say, why are you saying they're not symmetrical? Just use this word, but you might be in the exam and you might forget this word, asymmetry or asymmetrical. They are all asymmetrical, which means they're not symmetrical molecules. We now lead into discussing their shapes. So, both ethanol and I'm just going to call it CH3O CH3 because I can't bother to name that one. And you should do the same. If you can't work out the name of any of these, just refer to it by how they've shown the structural formula in the table. So both ethanol and CH3O CH3 are bent shaped around the O atom, and ethylamine is not tetrahedral. It's going to be, because nitrogen is, yeah, it's going to be pyramidal. And I can't spell that. Pyramidal. There we go. And ethylamine is pyramidal. It's actually trigonal pyramidal, but yeah. So that also contributes to why they're polar. Now we want to get on. That should have got all the marks. Have we talked about the electronegativities of the atoms? Yeah. So now what I want to do is tick through. Right, let's hit my green cross ticks. Explain why all three molecules are polar. We've talked about that because they're electronegative, blah, blah, blah. Why is ethylamine the least polar? We've said that here. So ethylamine is also polar. However, ethylamine contains, so it's less electronegative. So we've said why it's the least polar. Have the relative electronegativities. Yes, we've talked about the relative electronegativity. And we've also talked about the shapes. So there we go. Now, just for those of you that are like, well, how did I know the shapes were bent? Well, if you think of ethanol, so ethanol has this shape, CH3, CH2. Then we go to the oxygen, and remember oxygen normally when it's only got two bonds, which it normally has two lone pairs around it. And so that, just like a water molecule, is going to give it the bent shape. And then you're going to get the same thing going on with the CH3O CH3, and it's going to be like this. Okay. And then when you look at ethylamine over here, the ethylamine, you've got the nitrogen with one lone pair. Remember, nitrogen's in group 5 of the periodic table, so it's got three bonded pairs and a lone pair. And when you have that situation going on, you are going to form a pyramid, even though my pyramid looks a little shaky there with, whoa, with that bond there. So what I want to do is make that bond a little straighter-ish, right? So there we go. We got our pyramid. I could color that. Yeah, we could like block that and then do the old line thing there if we want. But you get the idea. That's just to explain those shapes and the molecules, how we came up with those shapes. All right, let's move on. No need for me to have a sniff every 5 seconds. I've got a bit of a cold at the moment, so in all my videos, I'm like, I'm sniffing away like a lunatic. Okay, last bit, last bit, last bit. So here we go. 5.3, explain the trend in boiling points of the three compounds. Refer to intermolecular forces in all three compounds. Do you remember they said that they have the same amount of electrons? So they don't give a mark for this on the mark scheme, which I find annoying, but same electrons. So same van, oh my gosh, the Waals forces. So that's, I guess they say explain the trend, and this doesn't play a part in the trend because they've all got the same van der Waals forces in all molecules. So they don't give you a mark for that. I thought I'd just explain that's the relevance of the electrons. It should lead you, don't talk about van der Waals forces and the size of them because they've just told you they've all got the same electrons. So they're kind of leading us away from talking about that. But what we do have is both, whoopsie, ethanol and ethylamine have hydrogen bonding. So if you remember, there are three types of bonds that do hydrogen bonding: hydrogen fluoride, hydrogen with bonded to a nitrogen, or hydrogen bonded to an oxygen. So both ethanol and ethylamine have hydrogen bonding. The strongest intermolecular force, and so have higher, whoa, boiling points. However, as O is more, remember we said this in the last one, it's more electronegative than N, ethanol has the strongest H bonds, right? So these two have got H bonds, but ethanol has the strongest ones because its H bonds are based on the OH bond. Right, what about the CH3O CH3? This has no hydrogen bonding. And you might say, but it has an O and it has an H. How can it not have hydrogen bonding? The O and the H are not directly bonded, so don't make that mistake. This has no hydrogen bonding. Oh my gosh, I can't even write this properly. This is, it has, oh my days, it has dipole, dipole, permanent dipole, dipole, um, intermolecular forces only. Not temporary, but permanent. So permanent. Temporary dipole-dipole forces, a bit like Van der Waals forces. So there we go. And that explains the 3 marks. So I would say the marks here are for pointing out that ethanol and ethylamine both have H bonding, pointing out that ethanol has the strongest hydrogen bonding, and then saying that CH3, OCH3 only has permanent dipole-dipole intermolecular forces. And I probably should say these are not as strong as H. Just in case I hadn't made that clear, these are not as strong as hydrogen bonding, which explains why they're more easily overcome and hence the lower boiling point. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.